Now, this is the second part of this video talking about the acceleration of a body in circular motion. And the first video started by talking about acceleration of a body in simple harmonic motion. That it has two different accelerations. We call them the centripetal acceleration. Why is it called centripetal acceleration? Because the acceleration is directed towards the center of the circle. Centripetal means center seeking, and also have the tangential acceleration which acts along the tangent to the point on the circular track or curve. Now, once again, I want to explain this centripetal acceleration in a different way that should be a bit clear and understandable. Centripetal acceleration, center seeking acceleration. Let's consider a body moving in this circle of center O and radius r. Let's say at a given time t, or t is equal to 0, we have this body at point A. Okay, this is the radius vector r. Let me use small letter r for that. Now, after some time t, the body has moved from point A to point B. Okay, moving in a circular motion with a constant speed. Let's say the speed is constant. The body in question, or in this diagram, moves with a constant speed is not changing, a constant speed in terms of magnitude. The speed is constant. Let's call that V. But let's look at it at point B or at point A. This speed has direction. It is directed along the tangent at A. So, which means this is a speed that has direction. You can call that velocity. So, I would say the velocity of the body at point A, I denote that with VA, different from just the speed v. So in terms of magnitude, because velocity is the algebraic or vector sum of magnitude and direction of the body. So if the body has both magnitude and direction, we say it has velocity. But if it has only magnitude, we say it is just speed. Now when the body goes to point B, you can see that the tangent at B is directed along this line. And let's say this is direction of motion. Okay, the angular velocity is this way. And if you check up, you discover that the direction at A is not the same as direction at B. So I can denote the speed at B or velocity at B as VB because the direction has changed. And before a vector quantity can change, there are two things. Either you change the magnitude while you keep the direction constant, like when the body is moving along a straight line with a constant speed. But if I want this body to change its velocity, either I'll keep the direction constant, let it continue in a straight line, but the speed changes. At this point, the speed is maybe 1, at this point, the speed is 2, at this point, the speed is 3. It means that the velocity of this body is changing because the magnitude is changing. I can equally keep the magnitude constant, but this body will now be moving in along a track with changing direction. The speed there is 1, or let's say 5. When it gets here, the speed is still 5 in magnitude. When it gets here, the speed is still 5. But you can see clearly here that the directions are not the same. We always draw a tangent at that point. The direction of the tangent gives the direction of the velocity at that point, direction of motion at that point. So this is another case where the velocity is not constant because the direction is changing, though the magnitude, which is speed, is constant. Okay, come back here now. We can see that because in terms of using the cardinal direction, this is like pointing northeast, and this is pointing almost or roughly north. So there's change in direction. So that the change in velocity, delta v, is given as the final velocity, that's the one at B, minus the initial velocity, that's at A. Okay, you can see that now. And in vector way, just want to add this graphically. We see that a vector B, VB minus VA, which is my change in velocity delta V, is same thing as VB plus minus VA. You can see that now because in vector manipulation or whatever, we say that this positive sign represents followed by, that's vector B followed by A. And since we place this as negative, it means that we're going to find the negative vector of VA. This is positive VA. So negative VA is a vector that points, that is parallel to VA, but points in the opposite direction. This is my minus VA vector. So how do I add that to VB? Because if I bring this out now, this is my VB. Let me draw it here. This is my VB, almost pointing north, roughly north. And then my VA is pointing this way, followed by, I'll lift this my VA vector minus VA vector and place it such that it follows vector VB. This is vector B followed by A. So the result, which is my change in velocity, you know, you can see clearly here that it's pointing towards the center of the circle. This is the center. If I bring this one here, just as it is now, translate it, it points towards the center. And then that's why the acceleration too is pointing towards the center of the circle. And the reason why it is called centripetal acceleration. Okay, so if this my angle theta here, I can place it here, this is my theta. And in terms of magnitude, I can draw this diagram in terms of magnitude only. Of course, the magnitude of the velocity remains the same because remember I told you that this body moves with a constant speed. The speed is constant in terms of magnitude, but in terms of direction, it's not constant. So in terms of magnitude, I place V here, also place V here. Now, if this angle theta is small, it follows by tan theta, it will be equal to theta. If angle theta is very, very small, let's say less than 1 degree, 0.5 degrees, 0.2 degrees. Okay, but what's tan theta? It's like saying this is my change in V. So that my tan theta, which is equal to theta, is given by delta V opposite over adjacent over one of the V's. So that is it. That's my tan theta. Now recall again that theta is given by omega multiplied by t because omega, which is angular velocity, is angular displacement over time. So I'm going to replace that here. Let me come out this way. So I have omega t is equal to delta v over v. I'm going to rearrange this equation so that I bring my t this way. So I have delta v dividing both sides by t divided by t equals, bring v to this side, that's v times omega. So the ratio delta v over t, that is change in velocity, which is the same thing as the change in velocity over time. That's the same thing as my centripetal acceleration AC, which is given as b times omega. But also know from this relationship that v is equal to omega times r, relationship between angular velocity and radius of the circle. So if I make substitution, if I substitute for v, I'm going to have this equals omega squared times r. Or if I have to replace omega, which is equal to v over r in this equation, I'm going to have centripetal acceleration AC equals v squared over r. I'm going to use this lowercase letter r. Okay, so that gives the another way of looking at it. Deriving the expression, explaining the centripetal acceleration. That this acceleration is towards the center of the circle and is given by this. So one thing about this is that if a body is moving, let's see the application. If a body, for instance, if a body is moving with a constant speed, this is a case of uniform motion. When the motion is uniform, it means the speed does not change. So when you have a body moving in a circle with a constant speed, that is v is equal to constant in magnitude, it means that the centripetal acceleration is not zero. It is given by v squared over the radius of the circle. But tangential acceleration is equal to zero when the speed is constant. Recall that this speed acts along the direction of the tangent at every point on the curve where the body is. Okay, so that is for uniform motion. Then for non-uniform motion, this is a case where the body is moving along the circular track with increasing speed. Let's say at this point A, the speed is 2 meters per second. When it moves to point B, the speed has increased to 3 meters per second. As it moves to point C, the speed has moved to 4 meters per second. This is the body moving along the circle with an increasing speed. In this case, we can say that the tangential acceleration is just change in speed over change in time, and it is not zero. It is not zero. you know. But to find the centripetal acceleration, that one is more like instantaneous acceleration. We have to know what it is at point A, which is different from what it is at point B. So centripetal acceleration will vary with location, with points, since the body has different speeds at different points on the curve. This centripetal acceleration will be varied, will be uh, a variable, so it varies. Okay, but this one is not zero, the tangential acceleration. And again, when the body is moving with some constant speed along this, when the speed is constant again along the circular track, I already said that the tangential acceleration is zero, but centripetal acceleration is not zero. It's not zero. What happens when the speed is increasing? When the speed is increasing, it means the acceleration of this body is in the same direction as the direction of the velocity. That is to say, the tangential acceleration is the same when the speed is increasing. So when speed is increasing, it means that A and V are in the same direction, direction, and otherwise they are in opposite direction. If this V is decreasing, that is, if the body is slowing down, it means tangential acceleration is acting in a direction opposite to it if the speed is decreasing. Okay, so that is how for this acceleration of body motion. Next video, we'll take one or two questions to help us understand this concept properly. Thank you. See you in the next video.